Ever wondered how large-scale computational tasks manage memory efficiently? Well, one of the key players in this game are sparse matrices. Let's dive into what they are and why they are so important. Imagine a matrix, a grid of numbers, where most of the elements are zero. This is what we call a sparse matrix. Now compare this to a dense matrix which stores all elements, regardless of their value. You can probably see that a lot of memory goes to waste storing all of those unnecessary zeros. So, how do we get around this? The answer lies in the clever design of sparse matrices. Instead of storing every single element, sparse matrices only store the non-zero elements along with their indices. This approach not only saves memory but also reduces the computational resources required for processing these matrices. So, by storing only these non-zero elements, sparse matrices save us a lot of memory and computational power. First up in the line of representations we have the coordinate list, or COO. Imagine a matrix as a city and the non-zero elements as buildings. The COO representation in essence is like a map, providing the precise location of each building. It does this by storing each non-zero element along with its row and column indices. This means that for every non-zero element in the matrix, the COO representation keeps a record of where this element is situated. Think of it as a list of tuples, where each tuple contains 3 elements: the row index, the column index, and the value of the non-zero element. The order of these tuples doesn't really matter, giving you the liberty to store them in any sequence. Now, constructing a COO representation is a walk in the park. You simply traverse the matrix, log the non-zero elements along with their locations, and voila, you have your COO representation. This simplicity is one of the significant advantages of the COO format. It's straightforward, easy to understand, and even easier to construct. But as with everything, it's not all sunshine and rainbows. While the COO representation is a breeze to construct, it may not be the most efficient for large matrices. Imagine a city with millions of buildings. A map detailing the location of every single building would be quite hefty, wouldn't it? Similarly, for a large matrix with numerous non-zero elements, the COO representation could become quite bulky. It might take up more memory than we'd like and slow down computations. So while the COO representation is simple and easy to construct, it might not be the best choice for very large matrices. The COO representation, while simple and easy to construct, might not be the best for very large matrices. Next on our list, we have the compressed sparse row, or CSR. This representation takes the idea of storing only non-zero elements a step further. It's an ingenious method that uses 3 arrays: data, indices, and indptr. The data array is where the non-zero elements make their home. They're stored in a compact linear fashion, reducing the memory footprint. The indices array, on the other hand, stores the column indices of these non-zero elements. It's like a map, pointing us to where each element belongs in the original matrix. Now, the third array, indptr, is perhaps the most intriguing. It's an array of pointers, each marking the start of a row in the data and indices arrays. It's like a bookmark, quickly directing us to the start of each row's data. But why is this representation so special? Well, the key is in the name, compressed sparse row. The CSR format is designed for efficient row-wise access. It's like having a superhighway for each row, allowing for speedy traversal and operations. Think about it. When you need to perform an operation on a specific row, you don't have to sift through irrelevant data. You simply follow the pointer from the indptr array to your row's starting point in the data and indices arrays, and voila! You have all the information you need right at your fingertips. This row-wise efficiency makes CSR particularly useful for certain applications. For instance, in scientific computing or machine learning, where operations often need to be performed across rows, CSR can drastically reduce computation time. Of course, the memory efficiency of CSR should not be overlooked either. By storing only the non-zero elements and their indices, CSR significantly reduces memory usage compared to a dense matrix. In essence, the CSR representation takes the basic concept of sparse matrices and optimizes it. It provides a roadmap to navigate through the non-zero elements swiftly and efficiently, saving both memory and computational resources. With its efficient row-wise access and memory usage, CSR is a step up from COO. Last but not least in our trio of representations, we have the compressed sparse column, or CSC. Much like its row-wise counterpart, the compressed sparse row or CSR, the compressed sparse column or CSC is a representation that's designed to store column-wise data. As you might have guessed from the name, this format is particularly adept at handling column-wise operations and providing efficient column-wise access. Now let's delve a little deeper into the mechanics of the CSC representation. This format uses 3 arrays: data, indices, and PTER. The data array is the storage powerhouse, housing all the non-zero elements of the matrix. It's arranged column by column, meaning that all the non-zero elements of the first column are stored first, followed by non-zero elements of the second column, and so on. This column-wise arrangement is what makes the CSC representation so efficient for column-wise operations. Next, we have the indices array. Similar to the CSR representation, this array stores the row indices of each non-zero element. So, if you've got a non-zero element in the second row of the first column, the indices array will have an entry of 1 for that element. Remember, we're starting from 0 here, not 1. Lastly, we've got the PTR array. This array contains pointers to the start of each column in the data and indices arrays. Each entry in the PTR array corresponds to the index of the first non-zero element of each column in the data array. So if the first column has 3 non-zero elements, the first entry in the PTR array will be 0, and the second will be 3. So why would you want to use the CSC representation over, say, the CSR or COO? Well, if you're dealing with column-wise operations, the CSC is your best bet. It provides efficient access to the data in each column and allows for quick computations. So, for column-wise operations, the CSC representation is your go-to. It's like having a well-organized toolbox where you know exactly where everything is. It makes your work that much more efficient and enjoyable. Now that we know the different representations of sparse matrices, why exactly are they so important? Well, let's get into it. Sparse matrices are invaluable because they enable us to handle large quantities of data more efficiently. Imagine having a matrix with millions of rows and columns, where the vast majority of elements are 0. Using traditional dense matrices to store this data would be incredibly wasteful, not to mention slow. Sparse matrices, on the other hand, only store the non-zero elements along with their indices, significantly reducing memory usage and speeding up computational tasks. But that's not all. Sparse matrices are also widely used in various fields. In scientific computing, for instance, they're used to represent large and sparse systems of linear equations that arise from simulations, finite element analysis, and optimization problems. Sparse matrices allow us to model these complex systems and solve them efficiently. In graph theory, sparse matrices represent adjacency matrices of graphs. Each matrix element corresponds to an edge connecting 2 vertices in the graph. Since most pairs of vertices are not directly connected, the adjacency matrix is usually sparse, making sparse matrices the ideal representation. In the realm of machine learning, sparse matrices come in handy when dealing with high-dimensional data. They allow us to store large amounts of data in a compact form, which is essential for training complex models. Natural language processing, or NLP, is another area where sparse matrices shine. They're used to represent document term matrices, where each row corresponds to a document and each column corresponds to a term. The non-zero elements indicate the frequency of each term in each document, making sparse matrices a perfect fit for this kind of data. So you see, whether you're dealing with large-scale simulations, exploring graphs, or processing language, sparse matrices are a powerhouse of efficiency. They allow us to tackle complex problems and handle large amounts of data with ease. Understanding how they work and how to use them is a key skill in many computational fields. Whether you're dealing with large-scale simulations, exploring graphs, or processing language, sparse matrices are a powerhouse of efficiency. Sparse matrices are a critical tool in the world of data science and computational tasks. We've traversed through the concept of sparse matrices, delving into their unique ability to store only non-zero elements along with their indices, a feature that significantly reduces memory consumption and boosts computational efficiency. We've also explored different representations, such as the coordinate list, compressed sparse row, and compressed sparse column, each with its own strengths and suitable applications. Our journey has shown us how these matrices can perform operations like multiplication, addition, subtraction, and transposition efficiently, even with larger data sets. We've seen the relevance of sparse matrices in diverse fields such as scientific computing, graph theory, machine learning, and natural language processing. It's clear that understanding these representations and operations on sparse matrices is indispensable for handling large-scale sparse data structures. So the next time you're faced with a mammoth computational task, remember the power of sparse matrices and choose your representation wisely.